Hello everybody. In this short tutorial, I will show you how you can find the natural frequencies and mode shapes of simple structure. We will start with a simple beam. Maybe we will change its constraint to a cantilever beam or a simple supported beam. Then we will move on to find out the natural frequency and mode shapes of a plate. And then we will see what are the natural frequencies and mode shapes of a disk. And perhaps we will see the effect of cutting a circle here at its center. Then we will move on to more complex structure like this bracket, which it works with other components like this mechanism. So this component, we're going to see if I change and optimize this component using topology optimization to a more optimized shape in terms of its strength and weight, which of course we have to now make it by additive manufacturing. But in this tutorial, we will see how changing the shape it affects its natural frequency and mode shapes. And by the way, if you are interested in learning how to get this optimized shape, you can check my other tutorial on generative design using Fusion 360, which I'll put the link below for you. Let's get started. So I have a cantilever beam here, which its length is 250 millimeters, width 20 millimeters, and its thickness is 5 millimeters. The material is steel. Let's make a cantilever beam. First step, I switch from design mode to simulation. Here, I check modal analysis and I create the study. So first step, I need to select my material. So I click on study material. I'm going to go with steel and I can find or modify its module of elasticity, or depends on the material that you have, you may change it. Next, I need to apply the constraint actually. My constraint, so if I want to make a cantilever beam, this part has to be fixed here. So over there, I select fix and then hit OK. So we'll see there is this symbol of lock at there. Now I have a cantilever beam. Next step, if I have a load, I can apply the loads, but we're just going to check the natural frequencies and mode shapes, so we don't care about the external forces. So I'll click here, and then I click on solve, or perhaps before that, I can click on manage, setting. Over here, I can decide if I want to get more accurate result on the mesh, and in general, I can select how many mode shapes I want. Let's go with 8. All right. And then I click on solve here. So it will solve it on the cloud and then click on solve one study. So it asked me to have a name for it. Maybe we should have saved the file before. So it starts solving it. It may take a couple of minutes. I'll be back in a couple of minutes to check the result together. Well, it seems the results now are available. I click close. Now I can look at the result. If I look at the side view, I can see the deflection here, and at the bottom here, I can see the first mode. Perhaps I can increase or adjust the actually the deflection to 2x, and maybe I can also look at the motion here. I click on two-way, and then I can play actually the mode shapes. So that's my first mode, and its natural frequency is about 68 Hertz. I can change to second mode shapes, and the second mode shapes is on the perpendicular plane, as you can see it with that natural frequency. Let's move on to the third mode. Here is the third mode of the cantilever beam. And as you can see, here we have a nodal point, and here is the fixed point. On the same plane, let's look at the mode number 5, which is a torsional. Mode number 6, it's in the plane. Mode number 7, it's a mode. And as you can see, these points are the nodal points. Well, and with each, we can, of course, see the natural frequencies in hertz. Let's move on to a different structure. Perhaps we are going to have similar cantilever beam. Let's quickly model it. But this time, I'm going to make a simple beam. So the length, or let's go with the thickness 5, and the length here 250 millimeters. And I'm going to have the thickness to be 20 millimeters. So it's exactly similar to the other beam, but I'm going to see if I change the support at two end, what will be the result. So similarly, I click on modal frequency and create a study. I keep my material as is, which is steel. Now for constraint, I select this end. Well, for this end, I change my constraint to pin, and this pin can radially rotate and also axially. We are allowing it to move. Or perhaps we can just fix it there and we just allow it to rotate axially there. Well, I realized if I want to pin support there, I need to create a structure there. Let's just quickly go back to the design. I'm going to select this face, and not going to be very accurate, but simply I'm going to create a bearing there. Let's say diameter 2.5. And similarly, on the other side, diameter 2.5. Again, this is just for the demo, and I'm not going to be exact. So now I select that side and this side, and I'm going to create a cut. All right. So now let's move back to the simulation. So for constraint, I'm hoping this time I can select pin over there. And yes, it seems it's working this time. So rotational there and rotational there. Okay, so now I have a simply supported beam. And I'll move on and click solve, create solve. And let's just put the name simple support beam. And I click save. So again, it will solve it on the cloud. It takes a couple of minutes. So we'll be back in a couple of minutes. It seems the results are ready. I close that. And over here, I'll take a look at the first mode. Let me just go to the perspective view. So as you saw, we didn't put any constraint on that direction. And our first mode is a rigid body mode. If I click on that animation, so my first mode is a rigid body mode, but I could have constrained it in axial. So then I wouldn't have that rigid body mode. But that's also a good thing to know. So I'll select my second mode. Here is my second mode, which in theory, we know this mode is half sine. And we can see the shape is almost half sine. So let's check the third mode on a different plane, but we are interested in this plane. So that's my fourth mode, which right at the center, we have a nodal point, and the shape is complete sine mode. I can further explore other modes like this fifth mode, which I have two nodal points right there, and each of them contains the natural frequencies. So far we saw the cantilever beam and the simply supported beam. Let's move on to now, let's do the modal analysis for a plate. So we'll repeat the process. I'll click on simulation and I check the modal frequency. We stay with the same material, which is steel. Now I have a plate. I can measure its dimension. So if you want to get the same result and compare your result, 150 millimeters its width, and its height is 90 millimeters. And the thickness, let's just quickly measure the thickness, is 2.5 millimeters. Well, we need to select a constraint similar to a beam, let's say a structural constraint. Perhaps I decide that one side of it to be fixed, and let's have fun and maybe also constrain that side. So, and we'll let the two other sides to be free. And click OK. And then I solve the problem. Similarly, I need to solve it on the cloud, create a study, and let's just put a name, save. And it will take a couple of minutes. We will be back when the results are ready. Well, the result seems to be ready. Let's take a look. Here is our plate and the first mode. Let's see how it looks. So as we see, we constrain these two corners, and the first modes is very similar to a cantilever beam. If I look from the side view, and similarly, if I look at this side from this edge, you see the behavior is very similar to a cantilever beam, as this corner is moving back and forth. Let's take a look at the second mode. So here is the second mode. And again, second mode, interestingly, from this view, we can notice this edge is behaving very similar to a cantilever beam, right? Because this edge is being constrained, and we see it's more like a cantilever beam. But this edge is very similar to the first mode, and we have a nodal line here rather than a nodal point. The entire line here is constrained. I can check higher modes. So now this mode, you'll see we have a line rather than a nodal point. I have a nodal line, which is more like a curve here. Fourth mode. Here is my fourth mode and fifth mode. So we'll see as we go to higher modes, the shapes become more complex and maybe more interesting. And here is the eighth mode. Now the eighth mode, we'll see the motion on this side is very similar to a cantilever beam, but of course adapting to the shape of this plane or to this plate. And with each, we can see the frequency. Now let's move on and perhaps let's take a look at the mode shapes and frequency of a circular disk or a disk in simple word. I'll go to simulation and a modal frequency, create a study. I will keep the material as it is. I need a constraint, a structural constraint. Let's fix perhaps this inside edge. So we'll fix that one. We'll pretend that it's more like a clamped circular saw. So it's fixed inside. And now let's solve it and find the mode shape of this system. Solve this study. And we'll call this one disk. Save. It's going to take a couple of minutes. And I'll be back in a couple of minutes when the results are ready. Well, it seems the results are again ready for this case. Let's take a look at the results. So here is our disk, and our first mode is 205 hertz, about 205 hertz. Let's take a look at the shape of these. Well, it seems like this disk has one nodal line and these two corners going ups and down. Let's look at the second mode. Second mode is perpendicular to the first mode and has one nodal diameters. Let's take a look at the third mode. Third mode is, if I look at the side, it gets to a shape of like a mushroom or concave, convex, and it has a frequency, interestingly, 205 hertz. So first mode, the second mode, and the third mode, they all have the same frequency, which happen in this case, but necessarily it doesn't have to be that way. 1 and 2, yes, because they are just similar modes perpendicular to each other because of the symmetric shape. So fourth mode is very interesting. It has two nodal diameters, as you see, and its frequency now increased to 143. Going to the fifth mode, as you see, it's perpendicular to the previous one. And now going to the sixth mode, I have three nodal diameters, right? We expect the seventh mode to be very similar, but just rotate, becoming perpendicular. And eighth mode, you see the number of nodal diameters increase and the frequency also increase. It's one of those interesting geometries when it comes to the natural frequencies and mode shapes. And it will be very interesting to analyze this system when actually this disk is spinning. Let's say it's part of a circular saw and spinning, which is a discussion for future. Well, with that, now let's move on to a more complex shape. As I explained earlier, here we have a bracket that works with other components. Let me simplify it. So I have the main foundation. I have the bracket being fixed on this plate, and then there is another mechanism that working with. Perhaps there are some bearings, and here we have actually other supports there. So my goal here is to look at this component and actually conduct a modal analysis on this bracket. So I'll move on to simulation and I check the modal frequency and assume that my material is steel again, or perhaps I can check the materials quickly to make sure. It's titanium, in fact. So let's just stay with titanium for this case. So the titanium, um, most likely we expect to have very high frequencies. So we'll start with the structural constraint. In this case, these two bottom, if you recall, it was fixed on the surface. So I'll just fix it on the surface. And then over here and there, I have a pin actually joined, which this pin joint allow rotation, and I'll keep it as rotation there. And structural constraint over there. For this one as well, it's pin, and we constrain it to rotation and allow the axial motion. But perhaps we need to have more information depending on the mechanism and the type of bearings and other information. But for now, I'll keep it simple. And we don't need to worry about the forces. We will just apply the constraint, and we have the material. Now, simply, we will move on to solve it. Perhaps solving this one, it takes maybe a bit longer. So we will be back when the solution are ready. Well, it seems again the results are ready. I closed that one, and now let's look at our bracket. So the first mode is 657. You can read it over here. And as we expected, it's a very high frequency because it seems to be a stiff bracket, and beside it's made out of titanium. And the mode shape is, it seems, these two, actually, because it's symmetric, these two portion of the this bracket, they are moving laterally, as it seems, because if you recall, for the joint, we didn't fix them. Let's move on to the second mode. Second mode, again, because of symmetric, we see these two are moving away or getting close to each other. So going back to the first mode, so these two, they are moving in one direction. Harmonically, they are moving in one direction, but now they are moving in opposite direction. We'll see a little bit of bending there. Third mode, it seems a little bit extra motion at the bottom. I'm gonna move fourth mode. In fourth mode, we'll see deflection over there. And keep in mind, these are the mode shapes. It's not the deflection of this structure. It shows us a pattern that, and the frequency that if this system vibrates on those area. And this is the fifth mode. It is an interesting shape. It is as if somebody is dancing, perhaps. And I can move on to the sixth mode. And maybe 7 here. And let's look at the 8th mode of this system. All right. Now, with that, I'm going to move on to the optimized shape of that bracket that we saw. If you recall, earlier I said that the same bracket, if we use it, actually, if we use generative design to optimize its shape, and here I reduce the weight by 40%, which is again a topic that you can watch a video that I made on generative design, a simple tutorial that how you can actually achieve this sort of shape. But our objective in this tutorial is to compare the natural frequency and mode shape of this one with the other bracket. Both have the same function and the same constraint and the same material. So let's move to the simulation. So it asks us to create a static stress. Automatically, we'll just say no. For now, we will do a modal frequency analysis, create a study. So let's make sure the materials are the same because we want to compare them, not the material property. Let's study material. It's titanium, the same material as before. I need to select my constraint, similar to that beefy bracket. This portion is fixed. I have my pin constraint or joint constraint here. And then I have my constraint at inside there, a pin constraint. So as you see, I just constrain it for rotation and I leave the axial to be free. Okay, so, and I hit solve. So the solution start, I'll give it a bit of time. Perhaps it's going to take a few minutes. I'll be back when the solutions are ready. Well, the results are ready. Let's take a look at the result for this case. Well, here is our bracket, perspective view, the frequency, the first one, 3606, and then let's look at the motion. So it's very, very similar to what we saw for the other one, but now it's a bit, of course, different and more motions on the base as well. And the frequency is about 3000 hertz. Let's go back and take a quick look at the first frequency of that one. So it's 6500. It seems the mode on these two, the shapes are very close, but you saw the frequency becomes half almost. It's an indication that the stiffness of this one now, not just the stiffness, because we reduce the mass and the natural frequency, the ratio of stiffness to mass dropped by, the square root of that dropped by half because the natural frequency is about half. Remember, the natural frequency is a square root of stiffness over mass, roughly similar to a mass and a spring, but here, of course, we have a more complex system. So the second mode, these two are moving like as you see away and getting close to each other, and the frequency is very close to the first one, 3600. Let's go back and take a look at the second mode of that one, 6600. And yes, as you see, the frequency actually is half, almost half. The third mode, I can rotate it so you can have a better view from this side. And the fourth mode, now the mode shapes are a little bit different maybe, and that's because of the pattern. For example, the fifth mode on this one, as you see, only the middle part, because it has a low stiffness, is being excited. But on this one, we don't have like that fifth mode. Is a different actually mode shape, different frequency. Let's move on to, and again, that's because in the middle we have lower stiffness. Move on to the sixth mode. Again, the focus is on the middle, 7, and so on. So paying careful attention to the modes like the fifth mode, because it shows the weak area of the system, and the system, it means there's going to be a lot of vibration. A lot of vibration is going to be experienced If this mechanism is under a lot of excitation, let's say part of a machine that vibrates a lot, it means that middle part is gonna experience large vibration actually. Let's take a look at the eighth mode. Well, it's a different shape and a different frequency. Well, let's summarize. In this tutorial, we managed to take a look at this natural frequency and mode shapes of a simple structure like a cantilever beam, the mode shapes that it can get. We look at the mode shapes and frequency of a plate, and then we skip that one, and instead we just did the disk one. Remember, for that one, of course, you need to define what sort of constraint you have. You know what? Let's just quickly do the mode shapes for that one. I'm just going to do the simulation, modal analysis, and let's have fun. And this one, let's constrain maybe the outer edge, which makes sense for that scenario. I'm just going to grip edges here, and we can decide to either, I'm not sure if we can, yes, we can use the pin. It means we allow the edge to actually not being fixed like a cantilever beam edge, but be able to rotate. And I'll keep the material as steel, and I solve it and create a study and solve. Let's call this one solid disk. Save. And we will be back in a few minutes when the solution is done, actually. Our result is, it seems to be ready. Let's take a look. Our first mode is 0. It seems it's just a rigid body mode, but let's just make sure. So the disk moves ups and down. Let's go to the second mode. Second mode, it should be again a mode that the point in the middle moves a little bit. Let's go to the third mode, or let's take a look at the second mode. Second mode, my mistake, is again another rigid body mode. It just shows the in-plane motion. So we ignore the first two modes. So the third mode, which is the actual first mode, is a one nodal, and perpendicular to that one nodal, let's go to the fifth mode, a two nodal, and sixth mode is like that. Pay careful attention that this disk actually, when we create the joint or the constraint, we allow it for axial motion. And maybe that's why perhaps we got this weird result. Let's go back and actually delete this study. Just gonna, okay. Or we can keep it and create a new study actually. But I'm gonna delete it. And again, I'm gonna go modal, structural constraint, just to see the result and the difference. This time I'm gonna fix the edges, which makes more sense actually, more realistic actually. And then let's again solve, and hopefully soon we get the result and we can compare. And I will be back when the results are ready. Well, seems the result for this one is ready. Let's now take a look. Well, yes, it seems more realistic now. Our first mode is that mushroom shape or concave convex shape. It moves ups and down, as you see. And then we have the second mode, one nodal diameters. And we have the third mode, perpendicular, fourth mode, four nodal diameters. Remember, the edges are fixed now, right? Fifth and sixth. So with the sixth mode, I have two nodal circles. If you pay careful attention, there are two circles which they actually have no motion there, right? And eighth, that's a very complex shape. So you can compare this one with actually with the hollow disk. Seems its mode shapes are more interesting. So, and after that, we check the mode shape of a bracket that works with other components. We look at different mode shapes, and the same component, when we optimize the shape, you saw how it affects its natural frequency and mode shapes, the way that it moves. Well, thank you very much for listening. I hope you enjoyed this tutorial and you can apply it to any structure that you have. Remember, this is an important uh, part of design, especially if the component you design is undergoing uh, excitation, high frequency, because you want to avoid designing components that one of its natural frequency coincides with the excitation frequency because it causes damage, resonance, and um, a lot of issue with the machine. And thank you very much for listening. Have a good day.